Okay.
Okay, welcome to the first session of today on symmetric cryptography. Our first talk is key-reduced variants of 3KF9 with beyond birthday bound security by Yaobin Shen, Ferdinand Zibeiras, and Ferdinand will give the talk. Floor is yours. May I remind actually whoever is on Zoom, you can ask questions at the end, like raise your hands and ask them in person, please.
Thank you for the introduction. Good morning, everyone. So let's talk about lightweight cryptography. So lightweight cryptography is quite a hot topic recently. We've got many lightweight cipher that were proposed, more than 60. Some built by many entities. You may know Prison, Gift, Simon Spec. And lightweight cryptography also have competition to build authenticated encryption. So not only block ciphers, but block ciphers and modes of operation that provide both authentication and encryption. So the CISA competition at the lightweight portfolio, who saw Ascon and Acorn as the winner. The NIST lightweight competition also is still ongoing. We have 10 finalists. You may have heard of some of them, but it's quite an ongoing field of research. But what we're gonna talk in this paper is a lightweight MAC. So not authenticated encryption, but only authentication. So why would we want only authentication and not encryption? Well, in practice, it's actually not so uncommon to only want authentication. For instance, when you want to synchronize some machine, you might want just to send a timestamp, which contain no secret information, but you don't want an adversary to be able to tamper it. So MAC only application exists, and it's also an interesting topic to look on. And it's also quite rare. We don't have a lot of lightweight MAC. It's mainly block ciphers and authenticating encryption, but authentication only, it's not clear. So one might think, okay, I can just take any MAC and plug in a lightweight block cipher because we have a lightweight block cipher. Can work, but you have to be careful that lightweight block cipher usually have a small size. So it's so to reduce implementation cost, and so it's more lightweight. And if you take conventional MAC like CBC MAC or PMAC, you might run into a trouble because the mode of operation is only secure up to birthday bound, which concretely means if you have a 64-bit block cipher, it's only secure up to 2 to the 32 tag authentication. And recently we had the Sweet 32 attack that showed that 2 to the 32 is maybe achievable in practice. You can have real security threats if you use small block ciphers with a birthday bound secure modes of operation. And so what we might want is to design MAC that are secure beyond the birthday bound. A typical way to build MAC secure beyond the birthday bound and to keep everything deterministic is the double block hash then sum strategy, where you double the internal state size. So no, instead of having a n-bit state size, you have a 2n bits to avoid collision. That's because you actually have an attack which exploits collision in the internal state. So if you double the internal state, collision happen much more rarely, and then you can hope to achieve beyond Bose-Daimon security. You have a lot of proposals that follows this pattern, some SCBC, PMAC+, 3KF9, LightMAC+. I plot them there. So let's just go one by one quickly. You see some SCBC was the first of its kind. It's like 2 encrypted CBC that you just XOR at the end to get the tag. PMAC+, you have some parallelization going on for PMAC+ and LightMAC+, where you have one block cipher call per block of message and some field multiplication. And then 3KF9, it's also some encrypted CBC, and you just XOR the output of every step to get to the tag. So how about the lightweightness? Well, some CBC use 2 block cipher per block of message, so it's maybe not so lightweight. But you can see that PMAC+ and LightMAC+ and 3KF9 only use 1 block cipher call per message. LightMAC+ and PMAC+ have the advantage of being parallelizable, but they use some field multiplication also with all block cipher call. And 3KF9, we have left with 3KF9, which is like no field multiplication, and it works. So how can we do even more lightweight Mac mode of operation? Well, one try is to reduce the keys. So if you see in the previous slides, for some SCBC use 4 different keys, and everything here use 3 different keys. So we might want to reduce the number of keys to 2 or 1. And that people have done that. For PMAC+, you have 1K PMAC+, LightMAC+, 1K LightMAC+. And they still use a field multiplication, and you only need 1 key and everything works. So that's really great. What about 3KF9? Can we do a lightweight version with 2 or 1 key version of 1KF9? That's the goal of our paper. So has it been done before? Well, it's been tried before. So the first try was 1KF9, this one, with a field multiplication, and the fix function we just fix the last bits to 0 or 1. So that creates the domain separation. The proof of this was never completed, and later, actually, we found a Bose-Daimon attack. So that's that shows that this construction is actually not beyond Bose-Daimon secure. 2KF9 was also proposed. So it's just like 3KF9, but at the end, instead of having 2 different keys, you have the same key. But that's really, you have a big issue here, because every 1 block query will create a 0 tag. So if you see after pressing 1 block, the upper and lower parts are equal. And so if you pass through the same block ciphers, the equality will stay and the tag will be 0. So in other words, if you take any 1 block message and you guess the tag is 0, it's a valid forgery. And it's not clear how you can fix this. If you add fix function, just like 1KF9 to create domain separation, then you have the same attack as 1KF9, so Bose-Daimon attack. And the other thing you can try to fix this is to always start by encrypting a 0 block, so that even 1 block message will have at least 2 block cipher code, and the difference will be created. In this case, it avoids the single block attack, but you still have an issue where for some pair of messages, the probability that the event that the upper part becomes the lower part, so sigma x become lambda y, and the lower part becomes the upper part of the second message, so lambda x equals sigma y, is actually only an n-bit condition. So that will happen at Bose-Daimon. And if this happens at Bose-Daimon, then because you have the same block cipher, the same value will come, but inverted. So lower part becomes the upper part, and you get a tag collision. It's not. It's actually not a forgery, but that's a distinguisher, because tag collision will happen more time than you expect. So that's what we learned from previous attempts. 1KF9, you have fixed function to create domain separation, but it leads to many bad events that you have to consider that seems hard to avoid at birthday bound. 2KF9, you have to be careful on the analysis, simple analysis of sigma y equal lambda y, so the upper part and lower parts being equal. In the analysis, you can see it was written like this, so the equation was written, or the event was written like this with the 3 dots. But if lambda y is equal to 1, then the sum is like there's no thing in the sum, so 0 equals 0 it actually always holds. So you have to be careful in the proof. And plausible construction, where you encrypt a 0 block, you keep the symmetry between the upper part and lower part, and this leads to a birthday bound event that makes the proof impossible. So let's try to fix everything. How did we achieve 3KF9? So our solution is this, and I think it's pretty neat. It's with everything that can go wrong. We realized that a single doubling at the end was solving everything, and a single doubling is in any Galois field you can come up. It's simply a 1-bit shift and a conditional XOR. So it's very light, and it seems to solve everything. Finite field multiplication has no fixed points, so every 1 block call will never lead to equality between the upper part and lower part, except if it's 0, but that's really very low probability events. If you look at the equation, so the upper and lower part being flipped between 2 pairs of messages, you can check that it always leads to a two n-bit condition, so it just won't happen at birthday bound. This, we don't use fix, so we don't have an attack on 1KF9, and everything is fine. We just need then to do the security analysis, and we're done. The 1-key version, we use the same ID, just one field multiplication with the additional restriction that we need a prefix-free encoding. And it shouldn't be surprising, because if you look at the upper part now, it's like a raw CBC MAC. And we know that CBC MAC is only secure if it's prefix-free, if the encoding is prefix-free. So to achieve prefix-freeness, one typical way is to encode the length of the message as the first block, and then you process with the rest. So it's actually quite a light fix, but seems to fix everything. If you compare our construction with encrypted MAC, then it doesn't use any other key, and simply an additional n-bit states, a field multiplication, and 1 block cipher call per message. The security, however, goes up to q to the third over 2 to the 2n, while the security of encrypted MAC is only birthday bound, so q to the 2 over 2d. And this can be even further improved, maybe, because we don't have a matching attack. The matching attack use a 2 to the 3n over 2 to the 3n over 4 queries. So maybe it can be improved. We don't know. Same for 1-key version, so just the CBC MAC. It's really comparable. Just add a field multiplication, and you have the same thing. You don't need an additional key. You don't need much. So the proof ID really follows previous works ID. Just we try to look at what went wrong and to treat every case properly. So we don't have any mistake in our proof. But the idea is simple. It's for every message we want at least the upper part or the lower part to be unique. So we say we want at least one of the sigma or the lambda to be cover free, so they don't collide with anything else. this is the part that was hard, and then the finishing, when you prove it's cover free, it's really the same as other proof. It works well, and no issue so far in any proof on that part. So what does that mean? It means that we have to prove 3 main bad events. So we have to prove that sigma L equal lambda don't happen. That's fine, that's easy, we just did it together. Then we prove that for any 2 messages, it never flips, the upper part never becomes the lower part at the same time that the lower part becomes the upper part. So that would lead to a tag collision. So we also did it together. The equation has a rank 2, so it's 2n-bit condition, never happens. And then you have the condition for any 3 messages. So for 1 message, the sigma part appears somewhere and the lambda part appears somewhere else. This doesn't lead to an attack, but it makes the proof easy if this never happens. And this is a rank 2 equation. So that's also a 2n-bit condition. That's also a 2n-bit condition, but on triples. So that's where our bound comes from. So you have q to the 3 triples divided by 2 to the 2n. That's 2n-bit condition. So that's it. In conclusion, I showed you how to build a 2-key and single-key version of TRIKF9 that retains security beyond the birthday bound. And that's potentially possible candidates for lightweight MAC going forward. Thank you.
In the meantime, I have a question. Can you go back to the 1-key version, 1KF and 1KF9?
Yes.
Yeah. So the last 2, the upper one, is that really necessary? Because it's like CBC MAC with the last block 0. Right?
So is it necessary? Probably. I didn't.
You didn't check it. Okay.
I didn't check it, but it's probably necessary. You have to redo all the equation, but it's basically what introduced the difference between the upper and lower part. And you want to use or you finish the proof is really using this kind of mirror theory, right? You just have the same permutation, and if you remove that, you will have to use it using the previous block cipher call, and that might become tricky because the adversary can choose M2, and I'm not sure it will translate in the proof.
But intuitively, wouldn't it be like, so the lower part does not change, and the upper part now is not the MAC of M, but it's the MAC of M appended with zeros?
Yeah.
And you XOR the 2.
Yeah, yeah. No, that's a good question. That's worth looking at. But you have to be careful because the adversary kind of control what goes in the. So I wouldn't know right off the bat how this translates to our equations.
Okay, thank you. Any more questions? Any questions from Zoom? If not, then let's thank the speaker again. Okay. I destroyed it. That's okay. Are you yes. Our next talk is Jamming on the Deck by Norika Bauchuyetti, Johan Demin, Seth Hoffert, Gilles Van Asch, Ronnie Van Kier, and Gilles Van Asch will give the talk. Thank you.
Okay, good morning, everyone. Thanks for the introduction. So I will give a couple of words about the title because it might look like a bit of a mystery. So in our paper, we have two contributions. One is the jamming cipher, and the other one is the deck function. So the title kind of combines the two. But in this presentation, due to lack of time, I will focus more on deck functions than on the jamming cipher. Okay, that's the outline of the presentation. I will give you an introduction talking about primitives and modes in symmetric crypto, then introduce deck functions, talk about modes of operations on top of deck functions, and give some words about the jamming cipher. Okay, so in symmetric crypto, many of the schemes that we use today are using a combination of a primitive and a mode of operation on top of it. So this picture really illustrates this. So that's we have the C level that defines the interface between the mode and the primitive. So above you have the modes, below you have the primitives. And yeah, what I mean with primitives is objects for which you cannot prove the security. You only have the only way to have trust in primitives is by having third-party cryptanalysis. So by primitives, I mean permutations, block ciphers, tweakable block ciphers, key stream generators, and so on. So we have people working above the C level, that is designing modes, proving the security of modes, proving bounds on these modes. And then we have cryptographers working below the C level, designing primitives and doing cryptanalysis to make sure that they are secure. So it's a nice picture, but there are some cases, some ad hoc constructions that kind of disturb this nice picture. So there are ad hoc constructions that are not made of the combination of a primitive and a mode on top of it. So yeah, what I would like to illustrate is that some of these, or at least I think many of these ad hoc constructions actually are, so they require their cryptanalysis on their own. That's one thing. And the other thing is that they usually address variable input length or variable output length. So stream ciphers are one example of such a thing. There are other examples. So for instance, the Pelican MAC function that was defined by Diamond and Raymond. So it uses, so it's a MAC function. It uses the full AES block cipher at the beginning and at the end, but in between it only uses 4 rounds of Rindal. So you cannot call 4 rounds of Rindal an ideal component. But globally, this gives a MAC that is up to now up to the claimed security, and it's 2.5 times faster than CMAC, for instance. Another example is the monkey duplex construction. A variant of it is used by Ascon, for instance. And there, so it uses permutations, but as you can see, the numbers and init and duplex below the Fs are the number of rounds. So the number of rounds are specified at this level. So cryptanalysis, again, has to be done at the level of the whole function and not at component level. And one last example is the Farfalli construction that we proposed a few years ago. And so this builds a PRF, and using this PRF is built using a lightweight permutation. So F is, for instance, 6 rounds of the Ketchaka permutation or 6 rounds of the Zudo permutation, which again cannot be called an ideal permutation. But nevertheless, the global construction is secure as a whole. So, okay, there are 2 ways out of this. So either we could just ignore these constructions and let they remain ad hoc, or we can try to take things differently and say, yeah, what about, let's explore the possibility that we define a new kind of primitive to put all these primitives under the same hood, let's say, and see what happens. And that's the goal of this presentation. That I said. Okay, so I'm going to introduce deck functions. That's the new kind of primitives that I would like to define. So a DEC function stands for doubly extendable cryptographic keyed function. So it's a function that takes as input a secret key K, and then a sequence of strings. So it's not just one string, but a sequence of M strings, X1, X2, up to XM. And it's, so I said it's a PRF, so it's going to output random looking bits and potentially an infinite sequence of random looking bits. The notation might be a bit tricky, but so fk of x1 to xm is an infinite string, but I take as a convention that at bitwise two strings together, we take the shortest one as the length of the output. So on, the n bit all zero string plus fk of n, fk of x1 to xm gives you a string of n bits. And then there is this shift by q positions, which really means that we take the output bits starting from the offset q. Okay, so it's doubly extendable. So what I'm also requiring from a DEC function is that it's efficiently incrementable, both at the input and at the output. So for the input, it means that if I first compute fk of x, so just one string in my sequence of strings, and I keep some state, then the next time I need to compute something, the next time I need to compute fk of x followed by y. So I will pay only the cost of processing y. Okay, so I don't need to process x again, at the condition, of course, that I kept some state information after computing fk of x. And the same thing goes for the output. If I request n1 bits, and then if I need some more, I can just restart from there. Of course, I need to keep state, but then I can get more bits without computing all the first n1 bits again. So I would like to stress that I'm not defining a new construction like Sponge or Farfalli. I'm just specifying a new type of objects. So really a set of requirements. So functional requirements, what this function does, what kind of input it has, security requirements, it must be a PRF, and then some efficiency requirements, this efficient incrementality. And now the question is, yeah, that's nice, but what can we do with such a new object? Okay, so there are some trivial examples. It can be used as a stream cipher. You just input the nonce, so the DEC function, and you use the output as a key stream, and can be used as a MAC. You input the plain text, and you take the output as the MAC. But there are, of course, more advanced modes. So I would like to describe some authenticated encryption modes. We'll describe 5 of them with different sets of properties. So DEC plain, and then 4 different ones. I will just start with the simplest one, DEC plain. Okay, so DEC plain, the purpose of DEC plain is to do first simple nonce-based authenticated encryption. So to encrypt, what I mean with the message is a pair of associated data and plain text, but it can also support sessions. And by sessions, I mean that I can continue encrypting and authenticating further messaging, and by keeping state, every time I authenticate something, I'll authenticate everything that I've received or sent so far. So let's start with just one message. So a pair of associated data A1 and plaintext M1, P1, sorry. First call to the DEC function, I take A1 as the input string, followed by 10 for domain separation. And this gives me some key stream that I add to P1, and I get Z1, the encrypted plain text. Then at the next step, I call FK again with A1 again, but I don't need to pay for this anymore because it's already done. And I just add to that Z1 followed by 1 for domain separation, and the result I use at the tag. So the concatenation of Z1 and T1 gives me my cipher. So it's simple nonce-based authenticating encryption. Of course, A1 must be a nonce, otherwise the security breaks down. But the thing is that I can continue. I can encrypt further messages. So let's say that the second message is made only of plain text P2 and no associated data. Then what the plain specifies is that I need to input A1 10 and Z1 1 again, but I will skip the first T bits because I used them already in the previous iteration, and I would just use the next bits as key stream to encrypt P2. And then I append to the sequence of input strings. I append Z2, sorry, to get the tag, and I get my ciphertext Z2T2. Let's say that I get a third message just made of associated data, no plain text. So that could be just a confirmation, okay. And I want to have a tag on the whole thing. And then, so the DEC function input will be everything so far with WHPRY followed by 00. And that gives me my tag. So this DEC plane, also I wish to say that it works as bidirectional communication. So we could also say, take as a convention that every other message is sent in a different direction. So the first message might be sent from Alice to Bob, then the second one from Bob to Alice, and the third one from Alice to Bob, and that works. Okay, so it's nonce-based. Do we have other modes that are maybe more robust? And that's the purpose of these 4 modes DEC Jamboree. So we look at these 4 modes from the point of view of Firestone networks. So there are 4 modes, and it depends. The 4 modes tell you which rounds of this Firestone network are used or not. So the middle part, the middle 2 rounds, that's both, that's always present for the 4 options. But then you can add one on the top or not, and one on the bottom or not. So if you have jam, it means you have the first round, otherwise you don't have. If you have re at the end, you have the last round, otherwise you don't have it. Okay, so let's start with the easiest one, so DEC Bo. So with DEC Bo, we have just 2 rounds, and what we do is on the left side of the Firestone network, we just put T bits equal to 0, and the right-hand side we put the plain text. So the first iteration, I go with the plain text inside the Firestone network. That gives me a tag. And then at the next iteration, I use this tag in the second call to the DEC function. The output is some keystream to encrypt Z. So you have probably recognized the SIV mode, just expressed as a Firestone network. So DEC Bo is essentially the SIV mode with the support of sessions. So I don't explicitly make the support of session on the slide, but if you read the paper, you will find all the details how to have the full session support. Okay, so that's good, but this mode can be made more robust by also making sure that it's resistant against the release of unverified plain text. So let's assume that an adversary can get unverified plain text and can then control the value V and then get some random ciphertext decrypted, and then by XORing P and Z, he can get the key stream for any tag he wants, so he can do keystream harvesting. So to avoid this attack, we just add 1 round, so the re round, we get DEC Bo re. And the last round, what it's going to do is just to blind this tag so that this attack is not working anymore. So keystream harvesting is not possible anymore, and you might have recognized the RIV mode, but so DEC Bo re is essentially RIV mode plus session support. Okay, so we can further improve this mode, and the slight problem we have now is that on the left branch we must have T bits, and these T bits, T must be high enough to avoid collision. So typically, if you want to have 128 bits of security, you need T to be 256 bits. So you need to add your ciphertext expansion is 256 bits. Can we reduce this? So the answer is yes. We add 1 more round, so that now we have the full jamboree. And what we can do now with this extra round is we can spread the plain text on both branches of the Firestone network. So we have OT and then some bits of the plain text on the left side, and then PLAS and some padding on the right-hand side. Of course, we still need to avoid collisions on both branches, but we have some room for plain text. So it means that this T now can be just the security level. So if I need 128 bits of security, T can be 128 bits. So I reduced my expansion. So what the first round does really is to produce a value Y that is representative of the plain text. So not knowing the key, it's difficult to find collisions in Y. So the rest of the Firestone network was as before, except that what was the plain text before is now this plain text representative Y. And now to finish the tour of the 4 different modes, I'm now removing the last one. So I have DEC Jambo, and with DEC Jambo, I have something that is like SIV, but so with optimal redundancy. so it's slightly better than SIV. But since I removed the last round, I don't have resistance against unverified plain text anymore. Okay, so that gives me 4 different modes, 5 if you include deck plane. In the paper, we prove that they are all secure, but yes, they are secure under which model? That's the topic of the jamming cipher. So we really wanted to have some modes that that support this concept of sessions, and the model that was the closest to this idea is the OAE2 model. But yeah, the slight thing we had with OAE2 is that it actually defines different flavors of OAE2. You have OAE2 A, B, C, and then NOAE2, DOAE2. And that was a bit difficult for us to, to treat all that. So we decided to define a new model, and that's the jamming cipher. So we wanted to have something that is both operational and referential. In OAE2, you have some modes that are meant for game playing, and others are meant for modeling something at the higher level. We wanted to have a single model for both non-enforcing and non-misuse resistant modes. Of course, sessions, bidirectional communications, parameterized ciphered expansion, and multi-key support. And the result is the jamming cipher. So I'm not giving the details. Please go to the paper to have all the details. But essentially, it's similar to a pseudo-random injection model, but with the support of sessions. We show that it's close to OE by proving this theorem. So the jamming cipher can in one model you can kind of replace all the different flavors of OE2 with just this one. So that brings me to the conclusion. So I spoke about deck functions, and I think it's a nice new kind of primitive that allows you to. Well, I think there are 2 advantages. One advantage is that by including variable input lengths and variable output lengths inside the primitive, you can have modes that are simpler to define. Of course, it kind of moves the problem down to the primitive, but at the same time, by allowing to have variable input length at the primitive level, you can really put the safety margin where it needs to be. So you can use maybe reduce round things inside, and so in the end, it allows more efficient ciphers. And then the other contribution is the jamming cipher, which is a simpler model, and it's the model of choice for these deck-based modes. That's all I wanted to say. Thanks for your attention.
So, questions?
So can you go to some slide where bow is to be seen?
Okay. Go. Yes, both here.
Okay, then maybe jam. Sorry.
Jumbo.
Here. So I suppose this branching on the right side of the X is then XORed right after.
Yeah. So yeah, maybe I didn't mention, but only the first few bits of the right branch are XORed with the output of the deck function.
And intuitively, why is that needed?
So what we want to do is to connect to. So let's take this one. In this case, Y is the plain text. So you want to have something that on the right-hand side is really your plain text. If you change the plain text, your right-hand side branch changes. Now, if you go now here, your plain text is partly on the left, partly on the right. So you could imagine that, yeah, someone changes only P first, and then the right branch would be only P last, and you would get some kind of collision. But you don't get a collision because P first goes into this first round and modifies Y. So if you change P first, then you get a different Y. And if you change P last, of course, you also get a different Y. And combining the two, you cannot do because you don't know the secret. The adversary doesn't know the secret key, so doesn't know what is XORed into X. So that's the intuition.
Yeah, okay, thanks. Makes sense.
More questions? So maybe I have a question as well. When I first looked at your paper, I think I thought that you could express, for example, this construction as a encoder and cipher paradigm. You could see it in that way, that you're building first a cipher, and then you're doing some encoding to turn it into an AED. But that, yeah, like that feed forward attacks kind of seems to disrupt that, right? Or
so yeah, we directly focused on authenticated encryption. We could have first defined a wide block cipher, for instance, and then added some encoding, some redundancy to do the authentication. Yeah, I think we could still do it. There is no contradiction. It was just that we focused on authenticated encryption. Yeah, because there is a page limit.
yeah, okay. So did you compare then how your bounds compare if you do the proof one way or the other?
No, not really. I wouldn't.
Okay.
I don't know. I would have to check.
Okay. Thank you.
Thank you.
Okay, let's thank the speaker again then. Okay, so our last talk is a modular approach to the incompressibility of block cipher-based AED by Akinori Hosoyamada, Takanori Izobe, Yosuke Todo, and Kanya Tsuda. And Akinori Hosoyamada will give the talk. Floor is yours, thanks.
Action. I'm Akinori Hosoyamada. And this research is about white box secure AED modes of white box secure block ciphers. And firstly, I would like to explain the background of our research. So this picture shows the black box model where we usually study the security of cryptographic schemes or cryptographic algorithm. We assume there is an attacker and a black box oracle of the target algorithm is given. And we assume that the attacker makes some queries to the oracle, and the oracle will return responses. And here, the important thing is we assume that the attacker doesn't have direct access to the implementation of the algorithm. So this is the usual black box model where we work and study security of cryptographic algorithm. But in the real world, sometimes we have some problems with this black box model. The problem is, in the real world, there may exist a kind of malware, and this malware may intrude into personal computer or server where the cryptographic algorithm is implemented. And in such a situation, security results shown in the black box model guarantee no security about this cryptographic algorithm. Because this malware may leak some information about implementation to the attacker. So this is the real world. And white box cryptography is a technique to remedy such a situation. I mean, white box cryptography is a technique to protect data against attackers who may have full and direct access to implementations of cryptographic algorithms. And in white box cryptography, there are two major requirements. The first one is the resistance against the key extraction, and the other one is resistance against code lifting. Here, key extraction is an attack to recover the secret key, and code lifting is an attack to copy the entire implementation. And of course, obviously, the resistance against key extraction is mandatory. This is obvious, but the important thing is resistance against code lifting is also mandatory, because if an attacker can copy the entire implementation of the algorithm, then the attacker can perform every cryptographic operation arbitrarily. So the resistance against code lifting is also mandatory. And next, I'd like to explain about incompressibility. This is a security notion introduced by et al. And this is a security notion against code lifting. And very roughly speaking, and so very intuitively, this incompressibility formalizes the hardness of compressing cryptographic implementations while keeping functionality. And for instance, suppose we have an encryption algorithm EK, and this one is compiled to a large program P. And then we say that the program is incompressible even if the program is given to the adversary. It is hard to build a smaller program that is functionally equivalent to the original program P. And very roughly speaking, incompressibility means the hardness for malwares to leak useful information. So this is the basic idea of incompressibility. And in previous works, there are many variants of incompressibility. For instance, EncCom by Fook et al. And space hardness by Bogdanov and Isobe and so on. So there are many variants, but the basic idea is the same. I mean, the basic idea is the hardness of compressing cryptographic implementations while keeping functionality. And the good point about incompressibility or its variants is they are achievable without relying on special secure hardware. And these days, many special secure hardware like TPM are common in use. But still, there exist high demands for software-only solutions in various scenarios like cloud-based payment services. So we also focus on incompressibility. And next, I'd like to explain the motivation of our research. First, in previous works, there already exists secure and efficient incompressible block ciphers, but there is no mode of operation to convert them into incompressible AEDs. For instance, the famous GCM mode is not incompressible, even if it is instantiated with an incompressible block cipher, because once the hashing key for Ghash is leaked, then universal forgery is possible. And similar attacks also work for other modes like CCM and OCB and so on. And second, there is no incompressible AE scheme achieving both of confidentiality and authenticity without relying on special hardware when the leakage exists. And so a natural question is, can't we reduce incompressibility like security notions of an AEG mode to those of block ciphers? I think this is a natural question, but it seems new security notions are necessary for both of block ciphers and AEDs, because existing security notions do not seem suitable for reductions from AEDs to block ciphers. And authenticity notions achieved so far in the white box setting are only a kind of universal unforgeability, which is much weaker than what can be achieved in the black box model. So this is the motivation of our research. And these are our results. Firstly, we introduce new white box security notions for AED and block cipher and PRF and so on. And second, we show that a weak variant of public indifferentiability implies reduction between new white box security notions. And third, we show that the SIV construction instantiated with sponge-based PRF and the counter mode becomes a white box secure AEG mode of block ciphers. And fourth, we also introduced a new white box secure wide block cipher, I mean 256-bit block cipher, which we name space 256-16. This is a variant of space block cipher introduced by Bogdanov and Isobe. And we conjecture that this block cipher is secure with respect to our new security notion for block ciphers. And in our paper, we assume that malwares can be detected if they consume lots of computational resources or send huge data outside, but we assume nothing about hardware. So this is the summary of our results. And in what follows, I would like to explain details about these results. And firstly, I'd like to explain about our new security notions. And first, I'd like to explain what we took into account when considering how to define security notion for AEADs. And first, we wanted to define the security notion by using real and ideal distinguishing games, like various conventional AEAD security notions. And second, we imposed some limits on the amount of leakage or malware running time, expecting that malwares can be detected if the leakage or running time are large. And third, we consider security only after code lifting or only after malware stops, because no security can be guaranteed during code lifting or during malware is running. And fourth, we noticed that leakage means nonce repeat, because malware may leak valid plaintext ciphertext pairs under some nonces that haven't been queried by the attacker. So white box secure AEAD must be nonce misuse resistant in the black box model. And finally, we cannot prohibit the attacker to forward outputs from the encryption oracle to the decryption oracle. Such things is prohibited sometimes in the black box model, but in the white box model, we cannot prohibit this because malware can do everything. And taking these things into account, we finally decided to define our new security notion by extending the pseudo random injection security or PRY security. And here, please remember that we say in the black box model, we say that an AEAD scheme is a pseudo random injection or PRY if the encryption and the decryption algorithms are indistinguishable from random injection and its inverse. So the ideal object in this security notion is random injection. And so anyways, we defined the new security notion for AEAD, taking these things into account. And our security notion is based on PRY security. And next, I'd like to explain what the real world looks like. So there is an adversary, and we assume that first, this adversary makes some queries to the black box oracle of the AEAD mode or AEAD scheme to gather some information. And then this attacker produces a malware. And by any means, the attacker let this malware have direct access to the white box implementation of AEAD scheme. And after doing some computation, this malware outputs the leakage to the attacker. And of course, this A1 and this A2 are the same attacker or same adversary in the real world. So we allow A1 to send some data to A2. And we assume that the A2 again makes some queries to the black box oracle to gather some information. And finally, it outputs the final final bit string. So this is how real world looks like. And next, I would like to explain about the ideal world. Since we define the new security notion by extending the PRY security in the black box model, firstly, the black box oracle is replaced with random injection and its inverse. So firstly, the attacker makes queries to the random injection oracle and produces a malware. But here we have a problem. The problem is there is no white box implementation in the ideal world. So here we introduce a simulator. And this simulator is time unbounded and makes some queries to the black box oracle. And then this simulator simulates outputs simulated leakage to the attacker. And here, the goal of the simulator is simulate this leakage so that the adversary A2 will not distinguish ideal world from the real world. Okay, again, so the goal of the simulator is simulate the leakage so that the adversary will not distinguish ideal world and real world. So this is how simulator works. And again, it's finally output something. And so finally, we defined the new security notion for AEG like this. And we name the new security notion WHPRY. We say that an AED scheme is WHPRY secure if for any efficient adversary, there exists a time-unbounded simulator S making reasonable amount of queries to the ideal oracle, making the distinguishing advantage small. So this is our new notion for AEDs, WHPRY. And next, I'd like to explain how we can interpret this new security notion. So suppose we have an AED scheme, and this AED scheme is WHPRY secure. Then there exists a simulator making the distinguishing advantage small. Then this means a lambda bit leakage by malware can contain only lambda bit information of valid plaintext ciphertext pairs. And this further means that the implementation, white box implementation of the AED scheme is incompressible. And the privacy and authenticity lost by lambda bit leakage is only lambda bit. So this is how we can interpret our new security notion. And next, we also similarly defined new security notions for block ciphers and PRF and so on. In particular, we named the new notion for block cipher as WHPRP. And this is an extension of the black box PRP security. And we conjecture that the space cipher, block cipher by Bogdanov and Isobe is WHPRP secure with respect to some reasonable security parameters. And so next, our goal is to come up with an AEG mode of block cipher and reduce WHPRY security of the AEG mode to the WHPRP security of the underlying block cipher. So this is our next goal. Our next goal is our next question is how to reduce the security notion. But here in our paper, we showed that some variants of indifferentiability implies reductions between our new security notions. For instance, if the structure of a scheme is indifferentiable from the random object, then we can say that there exists a security reduction between new white box notions. And in fact, some weaker variants of indifferentiability are sufficient to show reductions. For instance, if we can show only public indifferentiability instead of the original indifferentiability, it is also sufficient to show reductions between white box security notions. And we also show that more weaker variant, which we name weak public indifferentiability, is actually sufficient to show reductions. And I would like to explain details about weak public indifferentiability, but I don't have enough time today, so please read our paper for details. And so anyways, to show reductions, it is sufficient to show indifferentiability or weak public indifferentiability. And finally, I'd like to explain what kind of AEG mode becomes incompressible. And also, I'd like to explain new white box secure incompressible block cipher. So this is the AEG mode we focused on in our paper. The mode is the SIV construction instantiated with a sponge-based PRF and the counter mode. And here, please remember that the SIV construction first takes nonce and associated data and message as an input and generates a tag by using a PRF. And this tag is used as an IV for the encryption part. And here, we assume that the PRF is instantiated as some sponge-based PRF, and we assume that the underlying primitive of the sponge is the incompressible block cipher. And in our paper, we showed that this structure becomes public indifferentiable from a random injection if the underlying block cipher is ideally random permutation. And as I mentioned before, public indifferentiability implies security reductions between white box notions. And so this public indifferentiability means that if we have a white box secure block cipher, then the entire resulting AEG stream becomes again white box secure. And very roughly speaking, we showed that the mode is secure up to 2 to the power n/4 black box queries. But here we have a problem. The problem is the space cipher, Bogdanov and Isobe, seems to be WHPRY secure, but the parameter n is only 128, which means the security of the resulting AEG stream is only up to 2 to the power 32 complexity, which is not enough for practical use cases. And so we introduced a new block cipher, which we name space 256. And this has the block length of 256. So the resulting AED stream instantiated with this new cipher becomes secure up to 2 to the power 64 complexity. And this cipher is based on the space cipher by Bogdanov and Isobe. And we conjecture this cipher is secure if the query and the running time of malware is less than 2 to the power 64, and the amount of leakage is less than 2 to the power 20. And we also implemented the resulting AED scheme, and the performance is about 530 cycle per byte on Intel platform. Of course, this performance is much worse than the usual AED mode like GCM AES, but still, we believe this is practical enough for real world use cases. And so finally, I'd like to summarize today's my talk. We introduced new white box security notions for AEG and block cipher and so on. And we showed that a weak variant of public indifferentiability implies reductions. And we showed that the SIV construction instantiated with a sponge-based PRF and counter mode becomes a white box secure AEG mode. And we introduced a new white box secure wild block cipher, which we named space 256. This is a variant of the space cipher by Bogdanov and Isobe. And finally, in our paper, we assume that malwares can be detected if they consume lots of computational resources or send huge data outside. But we assume nothing about secure hardware. That's all. Thank you for your attention.
Any questions?
Hello, thank you for the talk. Just so I understand the incompressibility security definition, is it releasing the key? You had mentioned before on another side that GCM is not compressible because if you release the Ghash key, then you could forge tags.
Sorry, I just could not hear well, so.
Okay, this one's better. For the incompressibility security notion, are you releasing the encryption key? Is that released to the adversary? You had said before that for GCM. For the AEG, for the incompressibility, is the key released to the adversary? And because you said the GCM is incompressible.
Yeah, GCM is not incompressible. And your question is, sorry.
Is the incompressibility security definition? Or maybe we can.
I'm sorry, I don't understand something. And yeah, I'd like to discuss offline. I'm sorry. Thank you.
Another question? It wasn't resolved. It will be taken offline. I think the question was like in the, which is also a question I had in the incompressibility definition, right? You made the claim that GCM is not incompressible
Yes.
because the key of G hash leaks.
Yeah.
Right. I think your question was in the definition of incompressibility. You leak the key. Is that correct?
Yeah, when considering incompressibility, we assume that the malware may leak some information about the key. But here we assume that the size of implementation is very large. I mean, the order of gigabytes or something. And we assume that malware, if the malware leaks such large, huge information outside, then such behavior can be detected and we can stop using that implementation.
So incompressibility means like leaking some information that will allow, that is less than the description of the scheme, that allows breaking the scheme.
Yeah,
So the key of the G hash, is in a way a compression of the scheme according to incompressibility.
So the incompressibility means just a small amount of data does not allow attacker to break some security notion, like authenticity or something.
Okay, yeah. I think that should answer your question. Or, yeah. More questions?
Thank you.
No? Okay. Let's thank the speaker again, and
Thank you. Thank you so much.
please don't leave. We have an announcement.
So first, to remind you, early in the morning, there is coffee on the 4th floor for those who needs it. Also, the rump session deadline for submissions is today at noon. And please, submit your summary to the hard crap. And finally, we would like to remind those those people that we owe you money, like people who have student stipends coming to come and talk to the reception desk. Thank you very much. Enjoy your coffee break.